Good afternoon and welcome to today's lecture on algorithms and data structures. In the last lecture, we finished lists with our comparison of array-based structures and linked structures. And then we started looking into recursion. So we saw that recursion allows us to do repetition. It's a different approach than loops, for example. We looked at how a recursion is executed, and we looked at a couple of algorithms. In particular, we looked at the binary search, which works on a sorted data structure and can find us a value or can determine whether a value is in or not our list in logarithm time. At that time, we said it is in logarithm time, and I said we would do a formal analysis, and that's what we discussed at the end of last week's lesson. We also looked at a concept that is called divide and conquer, which means you have a big problem that you cannot solve directly, so rather you break it into smaller problems, you solve them, and then you combine those solutions. And one classic example is Towers of Hanoi, but we will see many more examples of divide and conquer. Today, some students asked me in the lab about a problem which is in the Goodrich book that asks us to implement an algorithm that finds the maximum in a list, but not implement this by using a loop, but rather recursion. That's also an example of divide and conquer. And then we implemented the Towers of Hanoi. We compared recursion to loops, and we saw that memoizing is super helpful to speed up recursion. We also learned they're equivalent. Recursion and loops, they have the same expressiveness, but some problems you can pose more easily in a loop, others in a recursion. And if you can easily convert it to a loop, then do that, because it will probably be faster. But yet recursion is super helpful to describe certain divide and conquer problems very easily. And then we wondered, how can we determine the time complexity of a recursive function? And we want to use our O framework, but this time it works a little bit different, because we first need to describe our problem in terms of a recurrence relation, which we did here, for example, for binary search, because we said if we have the whole data set, we then look into the half data set in the next iteration, plus some constant work. And the base case is also constant when we only have one element left. And then we try to find a pattern by applying the recurrence relation over and over again. And once we find the pattern, which is down here, we want to know when this actually goes to the base case. So when n divided by 2 to the k is the base case, when this is 1. And the base case may look different in other recurrence relations. So it's not always 1, could be different, but here it's 1. And then we solve for k, we plug k into the pattern, and then we simplify it, and then we apply our own O framework to this term. And then we have the O complexity of our algorithm. We saw other ways how we can do that, where I think this is where we finished last time. And today, we will quickly look at this, and we will see that we have an algorithm here that is called do something. And do something works on a list, and we have a left and right index. We calculate the middle, and then if left is less than right, we do something on the left part and then on the right part. And then eventually we combine this. So we're doing a recursion on the left part on the list from left to middle, and from middle plus right to the right. Sorry, from middle plus 1 to the right. So we have a recursion and then another recursion, and then we combine this. And now we may wonder, how can we express this in terms of a recurrence relation? And how can we determine the complexity of this? it's not an algorithm that does anything specific. It's more just like a pattern for now. And there should be some more steps in it that would do something concretely. But we'll see throughout the next few weeks a couple of algorithms that fit this pattern. And they do something a little bit more concrete, but they do something on the left, then something on the right. And then they combine this. For example, a sorting algorithm would first sort the left and the right, and then we would merge this. But this is more like a template here, this algorithm, and we want to determine its running time complexity. It's different to binary search, because for binary search, we always just looked into the left or right and then recursively narrowed the interval we are looking at. But this time, we're working on the left, then we're working on the right, and they recursively go further and further and do this then on the left again and on the right again and break it down. And then we combine all of this. Do you have any maybe intuition what kind of complexity or which complexity this could be? If you, maybe without looking at the slides, if you have a guess what the complexity could be, send this to the chat. So we got a guess that this is O of log n. Someone says O of n. Okay. We will see. What we need is a recurrence relation that describes this. And then we can solve the recurrence relation. I will try to share my screen. Just wait a second. Somehow screen share is not working right now. My apologies. So now we got a screen share. So what we can say this time is we have our recurrence relation. And we can say, well, T of n is T of n half, which we look into the left part, plus T of n half, plus n, plus some constant, but the constant doesn't matter. Because we once look into the left, so this was the recursive call on the left, this was the recursive call on the right, and then we combine all of this. So we need to look into all the n elements again, plus some constant part for these checks, but that doesn't matter for now because that's irrelevant in this further analysis. So we look into the left recursively, then into the right, and we combine everything. We can simplify this a little bit, and we can say, well, this is 2 times T of n half plus n, plus we have this base case, which was before we just calculate or compute a middle and we don't do any further recursion. So this is where we are stopping. We say, well, if one element is just there, we're stopping. And again, the algorithm from before, it's much just like a template. It's not a concrete algorithm yet. But for this template, we can describe this recurrence relation. And now we can try to solve it. So we're just doing the same steps as before, because we're trying to solve it. So we say the solution of this recurrence relation is the following. Remember, we apply T of n. Well, first we write down T of n. And then we apply it to itself. I'm just highlighting this in red. And the plus n is from before. And now I'm applying the recurrence relation to itself. So this where I have T of n half, I'm applying this to itself. So it's 2 times T of n divided by 4, because n halved again, plus n half. Because just from before, it's this one, and we put n half in, and eventually we have n divided by 4 plus n half, because for this n, we plug in n half, so it's n half. We can try to simplify this term a little bit, and we can say, well, this is 4, because 2 times 2, t of n divided by 4, plus 2 times n half, so plus n, plus the, oops, sorry, hit something wrong on the screen, plus the old n from before, so they are the same. Now I've just simplified all of this. Now we can apply, because we need to find a pattern in this, we can apply the recurrence relation again to itself. And then this is 4 times, this time, for this one, so it's this time 2 times t of n divided by 8. And I have n divided by 4, which I put here, because I put in this for n. And here I have halved it again, and that's why I divided by 8. The pattern is now 8 times t of n divided by 8. We say 4 times n divided by 4, so plus n plus our old n's before. And if you continue this, you'll definitely notice a pattern, and the pattern is 2 to the k times t of n divided by 2 to the k plus k times n. Because for each call or each recursion, I'm adding one more n. Now we need to solve this recurrence relation again, because we want this term n divided by 2 to the k to be 1. So we're saying n divided by 2 to the k is 1. So n is 2 to the k. And obviously, and we've seen this last time, we know then that k is the binary logarithm of n. This solution now is plugged into our pattern. So we have this pattern here, and I'm writing down the pattern again, and then I plug in k. So t of n is 2, and I'm putting the k soon in red. First writing this out, and then the k. So it's k here, k, and k times n, just a pattern from before. I'm plugging in this k at all these spots now. So what I have is 2 to the power of log 2n times t of n divided by 2 to the power of log 2n plus log 2n times n. This was the red part, this, and this. And now we can try to simplify this. 2 to the power of log 2n is just n. This one here is, so I have 2 to the power of log 2n is n, and n divided by n is just 1. We've seen this last time in the last recurrence relation. And here, I just change their order just to make it look neater, and I write it's n times log 2n. And this term here, t of 1 is just 1, so it's just n plus n times log 2n. So I'm asking you, what's the O complexity of this term? It's O of, and I'm waiting for your solutions. in the chat. This is correct. It's n log n, because this is the larger term and the constant doesn't matter. So it's just n log n. So we have just solved another recurrence relation. And we will see soon, or probably next week, algorithms that follow this pattern, for example, certain sorting algorithms. And then we just add a few more lines and this algorithm does sorting. And then we know the complexity of that sorting algorithm is O of n log n. I know when you start solving recurrence relations, it takes a little bit of practice. This is something you should definitely practice. There's also some work for you on this in the coursework for the efficient calculation of the power function. In order for you to practice even more, there are a few more examples here in the slides of recurrence relations. They have nothing concrete to do with an algorithm. It's just recurrence relations, but they will give you a bit more practice to solve them. This one looks slightly different because it's t of 0 is 1 and not t of 1. Bear this in mind. And try to solve this at home. In my slides, there is a solution of how to solve them. It's a little bit more tricky, but eventually it's doable. And you will see what its complexity is. And there's even another recurrence relation. And this one is maybe more close to certain algorithms. And you're also tasked with solving this. And the solution is in the slides. But first try this without looking into the slides. So this is some help for you for recurrence relations. And here I even have a larger collection of recurrence relations. And for all of them, I assume that the base case is t of 1 is 1. We have seen this recurrence relation. It's the one that refers to binary search, or binary search can be expressed with this recurrence relation. We have just solved this one here. T of n is 2 times t of n half plus n. This is, for example, merge sort, or merge sort can be described by this. We've seen the solution. And there are more. There are more recurrence relations in here. One, for example, that refers to the towers of Hanoi. Tree traversal, you don't know yet what tree traversal is. It's something we'll be seeing in a couple of weeks. Sequential search, we've already looked at. This one can be described by a recurrence relation, and so forth. And your task is, for the ones you have not done yet, also try them at home. And always assume t of 1 is 1 for those, and try them at home. It will give you more practice. If you look into past exams, recurrence relations often play quite some importance in the exams. So if you know recurrence relations very well, and if there are recurrence relations this year in the exam, then probably you're quite good in solving them. There is a more complex recurrence relation that I have here. And this recurrence relation is, or it's not a recurrence relation yet, it's a function actually that we're trying to compute. Is a of n, and a of n is 1, where n is the values 0, 1, 2, or 3. And when n is greater than or equal to 4, then it's a of n minus 1 plus a of n minus 2 plus a of n minus 3 plus a of n minus 4. And your task is also to find the recurrence relation for this function and then try to solve the recurrence relation. But when you use the tools we have used so far, you will very quickly struggle solving this one. So you need to come up with a little trick. And maybe you can amend the recurrence relation a little bit. And my tip is, or my advice is, remember with our O complexity, we're trying to find an upper boundary. And if you have a recurrence relation for this function and you struggle solving it, maybe try to find a slightly larger recurrence relation that is a little bit on top of it or a little bit greater, and try to solve that one. And that one is then maybe very easy to solve, and you're getting an upper boundary, but all I want is from you a reasonable upper boundary. It's a little bit more tricky, but certainly something you should practice. And I think once you master a recurrence relation like this, or try to find the O complexity of a recursive function like this, then you have understood the topics that we have discussed so far very well. Now, I know solving recurrence relations manually takes some time, and it isn't that easy. Now you wish that there could be some way of automating this, of maybe that you have to take less pains to find the O complexity for recurrence relation. And it turns out there is something. It's called the master theorem. And the master theorem addresses a certain type of recurrence relation. It's very important. The master theorem does not work for every possible recurrence relation, but for the ones that have a certain pattern. And for those, we can actually solve them quite easy once we have understood the so-called master theorem, and we don't need to manually try to solve these recurrence relations anymore. So we have our recurrence relation T of n, and we also assume there is a base case like T of 1 or something, but the exact base case doesn't matter for here, for this master theorem. We just assume there is a base case for some n that is less than a certain boundary, that T of n would be theta of 1. And you see this theta here, not an O. The good thing is, for this master theorem, it will give us thetas, not O's. So actually something that is much more useful than an O, because it's much more precise. And if our T of n follows the following pattern, that we say T of n is some constant a times T of n divided by some constant plus some extra term f of n. If our recurrence relation falls into this pattern where we have some concrete value a that can be 1, it can be 2, whatever, and b by which we reduce the size of the problem, and so a is how many subproblems we are creating in the recursion. Like if we just have 1, then it's just a linear recursion. If we have, for example, a 2, that's the one we just saw before in the recurrence relation that we actually branch out, but that's fine. You have an a, which is the number of subproblems in the recursion, and n is divided by b, plus we have some extra term that depends on n. And some recurrence relations we have seen so far, they fall into this pattern. For example, this one here, for binary search, the one for merge sort falls in, but the one for the towers of Hanoi does not fall in because we don't divide n by something, we subtract something. Tree traversal would also fit in. So you see, some of these recurrence relations are actually suitable for the master theorem. And the master theorem now tries to, or in the first step, we need to calculate something that we call the critical exponent, or C-crit. And the critical exponent is calculated as the log B of A. Remember, A is the subproblems of the recursion, and B is by which we are reducing the size in the recursion, how much we are reducing in. So if we say log B of A is something like log A divided by log B, A is the number of subproblems and B is the relative subproblem size. So log A divided by log B. And depending on this C critical, which value it has and how it relates to something, there are 3 cases in the master theorem. And for those 3 cases, we need to do different calculations. But then in each of those three cases, we can determine the complexity of the recurrence relation quite easy. And we're starting with case one. Case one describes those recurrence relations which are leaf heavy. So we've seen before the concept of a recursion tree, that a recursion can be represented as a tree. And case one addresses the cases where we have, or case one addresses the recurrence relations where we have most of the work in the subproblems. So we say where the work of splitting or recombining what comes from the subproblems, if this is much less than the work that is actually done in the subproblems. And such a recursion tree is called leaf heavy. And we can look at that. Remember, we have our f of n. And this f of n is the work we would do for combining, for example, for this extra work for split combine, when we get the results from the recursion and we try to combine something, or this extra work. That is f of n. And if f of n is O of n to the c, that's what we will soon see some examples to make this more clear. But if this term f of n is O of n to the c, when this c is less than our critical exponent, and remember the critical exponent is the log b of a, if that's the case, then we can simply say t of n is theta of n to the critical exponent. There's obviously a long derivation of the master theorem and why it works this way. I'm not doing this now with you. Feel free to read the original paper from a couple of decades ago, but we will directly apply the master theorem to case one, to a sample recurrence relation. And then this will be more clear to you. So this is the master theorem, case one. And I have a recurrence relation for you that is t of n, it's a times t of n half plus 1000 times n squared. And there is some base case for which we know that the base case is theta of 1. But the exact base case here doesn't matter, as long as we know the base case is in theta of 1. If you try to solve this recurrence relation manually, it will probably take you a little bit of time, and it won't be that easy. But we can now identify all the relevant parts. We can see A is 8, B is 2, and our f of n is 1000 n squared. And we see that f of n is O of n's to the c, where c is 2. We also need to calculate a critical exponent. So C critical is a log B of A, the log or binary logarithm of 8, and this is 3. So the critical exponent is greater than 2. And that's exactly what we said before. We said before, if this value C is less than the critical exponent, or the critical exponent is greater than C, just reading from the opposite direction, then it is case one in the master theorem. And then we can say that T of n is theta of n to the C critical, which means it's theta of n to the third, because C critical is 3. So, do you think solving the recurrence relation with the master theorem is easier like this than solving it manually. If you think this looks somewhat easier, maybe thumbs up. If you think it looks more difficult, thumbs down. But if you think it looks complex, try to solve this recurrence relation on your own. It will probably take you a little bit longer. So I think using this master theorem, probably it goes quite smooth. There are now two more cases of the master theorem. So case one, we've just looked at, and we said we spent most of the time in the recursion and not on splitting and recombining. Now, case two, and there's a question here if how we can find out if an algorithm is leaf heavy. It's exactly by comparing C critical to C. So if C critical is greater than C, then it's leaf heavy, because C describes the work on splitting or on recombining, and this describes the recursion. And if C critical is greater than C, then it's leaf heavy. Now in case two addresses, and there's a question where we got the C equals 2 from. I've explained this, but I'd be happy to explain again, because we said f of n, which is this 1000 n squared, is O of n to the C. This term here is O of n squared. So C is 2, because you need to look at this term. Hope this helped to understand it better. Now, in case two, we address those problems where the work on splitting and recombining is comparable to the work in the subproblems. And this looks a little bit more complex, but it's just highly generic, because we can apply to all sorts of recurrence relations that fall into our original pattern. And we can say that, or when f of n is theta of n to the C critical times log n to the power of k. So this expression here means I calculate log n and I raise the log n to the power of k. So if f of n falls into this one here for a k that is greater than or equal to 0, then actually the work on splitting recombining is comparable to the work in the subproblems. And then T of n is theta of n to the C critical times log n raised to the power of k plus 1. If you want to see why this is the case, check the original paper where the master theorem was derived, but this doesn't matter to this introductory course because we apply the master theorem. We don't need to derive it. Now, in order, well, I know this looks complex, but in fact, it isn't that complex when you start using some examples. And I'll show you another example now for case two. You'll see it's actually fairly doable. So now we're doing case two. And we're just using the recurrence relation we had solved today manually. It's T of n, it's 2 times T of n half plus n. And this is the one we solved before manually. Again, A is 2, B is 2, and f of n is just n. And again, we need to look at this f of n. And we are wondering if f of n is theta of n to the C critical times log n raised to the power of k. This is just what we defined before. And in order for us to determine if f of n is in this theta, we need to calculate the critical exponent, C critical. And remember that C critical is log B of A, and it's actually just the binary logarithm of 2, which is 1. And now we wonder, is f of n this? And in fact, it is, because what I can say is, if I have n to the C critical, which is 1, so n to the power of 1, times log n raised to the power of 0, then this just becomes 1, and this one also just means I have an n. So eventually I can say f of n is theta of n, because I have put this is a 1, and this just disappears. It's also 1 when I set k to 0. So for k equals 0. Because if I have log of n and raise it to the power of 0, it's just 1. So we actually see that our f of n satisfies this constraint. And then we're almost done. Because we saw before in the definition of case 2 that then t of n is theta of n to the C critical times log n raised to the power of k plus 1. And we just plug in our C critical and k from before. So we say it's n to the power of 1 times log n, k was 0 plus 1. So it's just raised to the power of 1. So this is just theta of n log n. And we're done. And when we manually solved this recurrence relation before, we saw it's O of n log n. And now we actually got a theta thanks to the master theorem, which is even more handy. We can look at case 2 for another example. So again, case 2. And the recurrence relation is T of n is T of n half plus 1. This is the recurrence relation we saw when we looked into binary search. Again, we can investigate it. We see A is 1 because we could just write 1 times in front of here. Our B is 2, and our f of n is just 1. And now we have to wonder again, is f of n, or if f of n is theta of n to the C critical, okay, wrote C critical, correct, yes, times log n to the power of k. We need to calculate our C critical again, which is log B of A. So the binary logarithm of 1. Logarithm of 1 is always 0. So this here would be 0. And if our k is 0, so for k equals 0, we can just say, as before, we have our theta of 1. Because if I raise this here to the power of 0, it's 1. And if I raise this to the power of 0, it's 1. So f of n is theta of 1. And that's correct, because 1 is just theta of 1. So we have case 2 satisfied. And now we can say that T of n is theta of n to the c critical times log n raised to the power of k plus 1. This is theta of n to the 0, because c critical is 0, k is 0. So we just say times log n raised to the power of 0 and 1. This means it's just theta of, this here is a 1, times the log of n raised to the power of 1. So just log of n. So we see this is fairly doable, and we don't need to manually solve these recurrence relations. And I got a very good question here in the chat. If why k is always 0, it's only 0 in our examples. When I've shown you the definition of the master theorem, case 2, we said as long as k is greater than or equal to 0, then this works. Our two examples we saw, k was 0 in both cases, but it could also be a value greater than 0, like 1 or 2 or whatever. Feel free to come up with more recurrence relations to practice this. And you see, using the master theorem is overall not that difficult. You've seen these examples here for case 2. Now, the only thing is, there is a case 3. And case 3 is a little bit more tricky. Because now we've seen the cases like case 2, where the work for splitting and recursion and recombining is comparable. We've seen the leaf-heavy ones. So the last case left is the root-heavy ones, where the work for splitting, recombining the problem dominates the work that is done in the subproblems. So we could now condition on f of n in relation to c critical. We can say f of n is omega of n to the power of c, where c is greater than the critical exponent. So it's lower bounded by the greater exponent polynomial. However, if you look into the definition of the master theorem, that condition alone doesn't yield much information. We actually need another condition that this works. And this condition here needs to be true, where we say a times f of n divided by b must be less than or equal to k times f of n. This time we have a constant k, and the constant k must be less than 1. If this condition, in addition to the previous condition, holds true, then we can simply say that t of n is theta of f of n. It's a little bit more tricky because of this extra condition, and I will present you another example, and then we have actually mastered the master theorem. Case 3. Our recurrence relation is t of n is 2 times t of n half plus n squared. And again, we find our components. A is 2, B is 2, and f of n is n squared. So we can say that f of n is omega of n to the power of c, where c is 2. So we have our value for c. We can also calculate the critical exponent, which is log b of a. So the log 2 of 2 which is 1. So the critical exponent of is 1, which is less than c, because our c is 2. And before we said, when I read it out, we said c needs to be greater than the critical exponent. This is true. We've just read it from the left and said the critical exponent is less than c, or c is greater than the critical exponent. So looks okay for case 3 in the beginning, but we need this other condition. And this condition was something like, in general, the second condition was a times f of n divided by b must be less than or equal to k times f of n with some k that is less than 1. And we want to see if we can find a k. So this actually holds true. We can say that our a is 2. So 2 times f of n divided by b, which is 2. And our f of n is n squared. So we can put n half in f and square it. So we say this is 2 times. So we just square now n half, because this is what f of n does. So this is n squared divided by 4, because I square the n and I square the 4. And we want to find a k so that this term is less than or equal to k times n squared. And 1k for which this holds true would be simply k is a half. Because this left part here we could simplify, and we could just say n squared half, because I multiplied a 2 with this, so this becomes a 2. And then n squared half is the same as half times n squared. So, and then I have satisfied the equal part. I could pick a different k, that's fine, but this k is probably just the most convenient one. So I have fulfilled the other condition of case 3, and now I can say, well, t of n is theta of f of n, because this is case 3, and this is, so we have our f of n, which is n squared, so it's theta of n squared. So t of n is theta of n squared. So all these 3 cases are actually not that difficult. You're probably wondering whether you can remember them for an exam. I'll say more about the exam in a couple of weeks, but you can already find past exam papers in my Nextcloud. And in my exam papers, I always write, you can bring a one-sided A4 note sheet that is handwritten with notes of your choice. So handwritten, one-sided A4, and maybe those 3 cases of the master theorem or something you wish to write down, because you may not be able to remember those 3 cases. That's okay. Plus other things you could write down on your sheet. So you don't need to learn them by heart. Obviously, you need to understand those 3 cases, and you need to be able to apply them. Now, there are a couple of other recurrence relations for which the master theorem does not work. So the master theorem, it's very important, only works for recurrence relations of this sort. I have a constant a, I divide by a constant b, plus I have some other term on top. And there are many more recurrence relations for which the master theorem does not work. For example, this one here. I can say, well, let's start with this part. T of n half is okay. because B is 2, but the A is not a constant. A actually depends on N, so it's not a constant. So the number of subproblems is not fixed, and that's why this one doesn't work. This one here is also tricky because I have this part here at the end for f of n, and then actually I have a non-polynomial difference between f of n and n to the c critical. That's why such equations here don't work either. I could also imagine a recurrence relation like this. I say t of n is a half times t of n half plus n. But this here doesn't make any sense because I can have one subproblem or two subproblems, but I cannot have 1.5 subproblems or just a half subproblem. That doesn't work. That doesn't make any sense from our point of view, from a computation. And that's why here the master theorem will not work either. Or you could have like a negative f of n. And if you have a negative f of n, this doesn't work either because we always add time on top through the f of n. We don't subtract time. So here, the master theorem will not work either. This one here looks strange. It's something you will probably not come across in this course again. It's actually case 3, but it violates one of those conditions in case 3. And that's why it doesn't work either. So always make sure when you get a recurrence relation, only use the master theorem if it has this a, b, and f of n, and it's actually a valid one for the master theorem. If I ask you in the exam to solve a recurrence relation, and I don't specify which method, you can use the master theorem if it's applicable. You don't need to solve this manually unless I ask you to solve this manually, or if I ask you to use the master theorem, you're supposed to use it. But if I don't specify the method in the exam, you can pick the method as you wish to solve it, as long as obviously it's a valid method and the solution is correct. So, the master theorem is now done. I think you have mastered it. And if you practice it a little bit more, I think this could be a very helpful experience. When you look into algorithm books, you often see in a chapter on recursion something that is called backtracking. And backtracking is a general algorithm that finds you all or some solutions of a computational problem where you have some constraints. And you try to incrementally build your solution, and you go back to a previous candidate. You backtrack as soon as you find out that with some candidate, you have probably not reached a valid solution. You can imagine this, for example, if you try to solve a maze and you move into different directions and you branch out, but at some point maybe you have reached an end and you're not at the exit, so you want to go back and try a different route. That's exactly how you can imagine a backtracking algorithm. And backtracking is actually a highly generic approach. And what backtracking does in practice is actually you're building a search tree and you're reversing that search tree recursively from the root in something that is called depth first order. Depth first order is a term we will see in 2 weeks' time or so when we look into trees. For now, this term depth first order doesn't matter. I don't discuss the backtracking algorithm here in detail in this course because we have already discussed highly generic stage search algorithms in this course, like this highly generic shortest path and the highly generic lowest cost. And they, in fact, do something quite similar as backtracking. And that's why we'll not further discuss backtracking. Backtracking is a little bit a different approach and typically uses recursion, but our shortest path algorithm and our lowest cost, they do this for us already, so there's no need to discuss this here. And in a typical algorithms course or book, you would discuss backtracking, because if routing is discussed, it's often just the Dijkstra algorithm, which you would apply to routing. But we have not done routing, but we have done shortest path and lowest cost search in highly generic state spaces. And then as a consequence, we can also do backtracking. And that's why this is something that we can skip, because it's not necessary anymore to this course. But feel free to look up backtracking in a book or something. But I told you before, when we did this shortest path and lowest cost, I said they are highly generic and you can reuse them to many other problems. And this is the case here as well. Now, we've seen that recursion can be extremely expensive when you run it, especially if you have a branching recursion, for example, for the Fibonacci numbers. We had briefly looked at a concept that we call memorizing, so we can store the output of a function for a given input when it's deterministic, so we don't have to recompute it. And this helped us in the last lecture to massively speed up these computations. And I told you we would extend this a little bit. And today we are looking at dynamic programming. And in general, dynamic programming is a mathematical optimization method, as well as a computer programming method. And in general, dynamic programming allows us to simplify a complicated problem by breaking it down into simpler subproblems. If you look at dynamic programming, say from an optimization perspective or an operations research perspective, they discuss it in a slightly different way and probably in a broader view. But we will now constrain ourselves to recursive problems. And we want to speed up recursive problems by doing dynamic programming. And we're going to do this in two directions. We're going to do this in a top-down approach, which is very similar to this memorizing we have seen before. So top-down means we're breaking the problem up, and then we're splitting the problem into smaller ones. So this is top-down, come from the big input and try to split it. And the bottom-up approach is just the opposite direction, where we start building small solutions and we incrementally build them or compose them into bigger solutions. And then we stop once we have reached an adequate size. So these are just two different directions, bottom-up and top-down. And we will be starting with the top-down approach. And I will directly start with a piece of code, and I'll show you how this works. Actually, what we are doing now is we are not using our memorizer, but rather we will build our own memorizer in a very simple way. We are going to do this again for the Fibonacci numbers. So remember, a Fibonacci number of n is just the sum of the two predecessors. And we said the first Fibonacci numbers are 0 and 1. But this time, we are going to store this as a dictionary. So when n is 0, the Fibonacci number for n equals 0 is 0. And for n equals 1, the Fibonacci number is 1. And for 2 and 3 and so forth, we are going to compute this now. But once we have computed this, we're going to store this in our memory. So again, we have a Fibonacci function. And what we actually want to compute is something like the Fibonacci number of n-1 plus the Fibonacci number of n-2. We've done something like this last week, but we also need a corner case where to stop, and we had implemented these edge cases where to stop. And this time we're going to implement this a little bit different. So we will come to this return in a moment. First, I want to check if n is in the memory. And so I will check if n is in the memory. And if I write this, it will check if n is a key in the memory. And this is a dictionary. You remember them when we did an intro to Python like 5 or 6 weeks ago. We said this is the key and this is the corresponding value in a dictionary. In a few weeks' time from now, I will show you how you can implement your own dictionaries. But for now, this doesn't matter because we just use the default dictionary in Python. So I want to check if n is in the memory. So I want to check if n exists as a key in here. But if it's in, I'm actually fine. Then I can just return it. So I actually care if n is not in the memory. So I'm just inverting this. And this works perfectly fine with Python syntax. That's very close to human language. If value n is not in the memory, then I need to compute it. And I need to compute the nth Fibonacci number. And the nth Fibonacci number is actually the Fibonacci number of n minus 1 plus the Fibonacci number of n minus 2. Once I have computed it, I can return it. And I have just implemented the Fibonacci numbers with my own memorizer because I check if n is not yet in the memory, I will compute it and then store it in the memory, and then I will return it. And if it's already in the memory, I don't need to recompute. I can simply go to the return. And we can now say, well, what's the Fibonacci number of 10? It's 55. And remember, if I put in some very, very large value, this will probably never finish because at least if I implement this in a naive way, because in a naive way, it will just branch out and recompute the same subproblems over and over again. But with my memorizer that I showed you last week, once it's calculated for a certain n, it's stored in the memorizer. And we use the memorizer by using this decorator syntax. But here we're just building our own memory. And I will see if I calculate this, it's fairly fast. I can calculate a Fibonacci number of 100 in 55 microseconds. And I can now look into my memory, and actually all these Fibonacci numbers are stored in it now. The third Fibonacci number, or Fibonacci number for n equals 3 is 2. For n equals 10, it's 55, and so forth. And this is my top-down approach, because in my top-down approach, I'm first checking if my large n already exists. If it exists, it's fine. If it doesn't exist, I break it into 2 smaller ones. And these are the recursive calls. Say, if I call this now for 102. 102 is not in the memory yet. And it calculates this for 101. Wait, a recursive call for 101 and a recursive call for 100. But this one here is already in the memory, so it doesn't go down further. And for 101, it takes the Fibonacci number of 100 and 99, and both are in the memory already. So there will not be much of a recursion happening because it's just stored in the memory. And so we're just rebuilding this memorizer. This memorizer that we used last week is obviously much more advanced because it works for functions with multiple parameters. It's a cache, which will not get too big. But we have just built our own memorizer in a very simple way. Now, this is the top-down approach to addressing how to calculate the Fibonacci numbers. You can obviously use this for many other recursive functions and store this in the memory. If you build this from scratch, maybe just use that Python decorator in order to do memorizing, our LRU cache, because this is a cache and it can handle multiple parameters and more complex parameters. So you don't have to build this from scratch. But I've just shown you how it works. So this is the top-down approach. And we can now also do a different approach, which is a bottom-up approach. And in the bottom-up approach, we want to start building very small Fibonacci numbers first, and then incrementally compose them to make it to larger Fibonacci numbers. And then at some point, when we have reached a Fibonacci number for an n that is sufficiently large, we just stop. And this bottom-up approach can also be done. We can, for example, call this fib bottom. And fib bottom is, first of all, we need to check a corner case where n is 0, because we need to start with something. And if n is 0, it's just the smallest possible Fibonacci number, we return 0. And now we will calculate our current Fibonacci number from previous Fibonacci numbers. So if n is greater than 0, we need to do a little bit more. So if n is, for example, 1, we can say, well, our previous Fibonacci number is 0, and the current one is then 1, and we are returning 1. So I need a previous Fibonacci number, and this is the one I call 0. And now if n is 1, I could just return the sum of these two. But I need to generalize this a little bit. And if n is now bigger, I need to have the adequate previous and current Fibonacci number at hand. And the way I can do this is the following. I will have a loop, and I say for index in range of n minus 1. I'll explain you later why this is n minus 1 and not n. And I need to calculate now the next Fibonacci number. So the new Fibonacci number is just the previous Fibonacci number plus the current one. So previous and current is the new one. And I later want to return my current Fibonacci number. And now what I need to do is I have calculated the new Fibonacci number. Now I need to rotate among these variables because I want to have a fixed number of helper variables. I don't want to have n many helper variables because then it takes too much space, which is unnecessary. So I will now say previous Fibonacci number refers to the current one. So the one that was just current is now the previous one. And the new current one is the newly calculated Fibonacci number. And then I may have multiple iterations, and I'm always calculating that new Fibonacci number from the previous one and the current one. Then the previous one, or the one that was the current one, is then called the previous one, and current one is the new one. And I'm returning the current one. And we can see that this works. We can say fib bottom of 10. It also gives me 55. I've promised to tell you why I say n minus 1. I say n minus 1 because I already have this one more helper variable. I not just have one helper variable, but I have pre-computed already one of those from before. So I need to put in n minus 1 because I need one iteration less because of this one extra helper variable. And if I had, say, 3 or 4 helper variables that I need to store, then I may have to adequately reduce this n. If, say, this was something different than a Fibonacci number, maybe the sum of the last 3 numbers, I would probably have one more helper and then say it's n minus 2. But that's only a detail. And we see it works perfectly fine. And we can wonder which one is faster. We can say our fib was the top one. We can say, well, what's the Fibonacci number of 1000? Calculating this top down, which takes 1.366 milliseconds. And we can calculate this for the bottom one as well, or for bottom up, it takes 101 microseconds. So the bottom up tends to be faster. We can say this, we can also do this for 10,000 in the top down, which unfortunately we have reached a maximum recursion depth. We can say maybe 3,000, I don't know. So it's 1.36 milliseconds, but we have maybe already used the memory. So I'm just starting this from scratch. So I'm initializing the memory, and then I'm saying I'm doing the top down for 3,000. And this takes, unfortunately, I've again reached the maximum recursion depth, which isn't great. So for 2,000, it takes 1.49 milliseconds. And for bottom up for 2,000. So the bottom up one is faster. And for the bottom up one, I can also put in a much larger value, as you can see. And I don't run into this, that I don't run out or don't reach the maximum depth in the recursion. With the bottom up, I can calculate a very large Fibonacci number very, very quickly, because I don't need any recursion at all. And I don't have this memory. So I'm always starting from scratch for a new call of the function, because I don't have a memory, but I don't need any recursion. And the advantage of the top-down one is it stores the memory. So if you again put in a large N, it doesn't recompute it from scratch, but rather reads it from the memory. So this is also what we got here from one student in a chat. The top-down has the advantage that if I call it more than once, I have the memory. And maybe the code is a little bit simpler than the top-down, than the bottom-up, because the bottom-up, imagine you calculate a much more complex function, then the bottom-up would probably become more longer and longer, and the top-down one would probably be still much more readable. So they both have their pros and cons. In terms of their running time, at least for this example, the bottom-up is far faster, has less memory footprint, but not a memory where it's stored and recomputes from scratch. So they both have their pros and cons. There's a question if there is a recursive bottom-up approach. Well, yeah, you could repose this as a recursive problem, similar to the top-down problem. You could pose this as a loop and maybe emulate this via your own stack. You could do this, but at least for these kind of recursive or for these kind of functions, probably the top-down one can be written in a recursive way more easily, and the bottom-up one can be written more easily with a loop. But loops and recursions are anyway equivalent. So you can pose both of them just vice versa. Now you have seen that, or now you see we have finished the recursion chapter, and we are done a little bit earlier with the lecture today. Next week, I'll see you in the lab again, and hope next week we don't have any network issues like today in the morning, so the lab should go smoothly on site. In next week's lecture, we will look into sorting, and I'll show you how you can sort a list or some data structure and how you can sort it efficiently. We will look at various sorting algorithms. We start with very simple ones and then more complex ones, and then more complex ones we can again express very well as in terms of a recursion. When we wonder about their complexity, all we need are the recurrence relations, and we know now how to solve recurrence relations very well. Take a look at the coursework until next week and take enough time solving these recurrence relations. So make sure you're familiar with the master theorem, And my advice is look at all of these recurrence relations again, solve them manually, solve those that you're able to solve with the master theorem. And there are 2 more practice ones that you should look at. It'll just give you more exposure. And also this one here, it's a more complex one. And if you practice them very well, I think you have a good understanding of how to determine the running time complexity of recursive algorithms. And next week, with all this knowledge of recurrence relations, O complexity, and recursion, we can then continue with sorting. I wish you a good weekend, and I look forward to seeing you next week. Bye-bye.